In this video, we'll be demonstrating BuildBot, which is our final project for our CAP4621 class. So in most modern games, built-in AI bots rely heavily on scripted behavior and predefined rules. These bots don't actually learn from experience, which makes them super predictable and far less adaptive than real players. And this led us to the main question: can we train an autonomous agent to learn and adapt inside a fast-paced, unpredictable 3D game using reinforcement learning? The thing is, reinforcement learning today isn't advanced enough yet to handle the full complexity of Fortnite. Things like knowing which weapon to swap to, running away from Storm, and don't even get me started on building. The problem just becomes too large to solve in a single semester. We wanted to focus on a subset of core basic gameplay skills, such as movement, aiming, picking up items, all inside a controlled Fortnite environment. Our agent learns directly from screen input and improves through reward shaping, similar to how a player learns by trial and error. Our approach centers on proximal policy optimization, or PPO, which provides stable, reliable updates during training. We limited training to simplified tasks inside environments that we created using the Unreal Engine for Fortnite. And using these UEFN environments, this allowed us to isolate specific behaviors and measure learning progress more effectively. Moving on to our workflow, here's an overview of our entire system architecture. The whole pipeline forms a closed loop between Fortnite, our environment wrapper, the reinforcement learning agent, and the controller. When we start training, we run the train PPO file, which starts up our PPO agent. This agent is responsible for selecting actions based on the observations it receives from the environment. The agent sends an action request to our Fortnite env wrapper, which represents the entire Fortnite game as a reinforcement learning environment. Inside Fortnite env, we perform a screen capture step. So what this screen capture module does is it grabs the current Fortnite frame and downsamples it to an 84x84 grayscale image that the agent can process. The environment then extracts this cropped 84x84 grayscale frame for the policy network, along with the original color frame for computer vision based detection. This is also where our reward functions operate. We run HSV masking to check whether an item or enemy is visible, and we assign rewards accordingly. And to keep the reward detection consistent and reliable, we added a custom green screen HUD flash inside the game. Whenever the agent picks up an item or eliminates an enemy, this bright green overlay appears, and because it's easy to detect through HSV masking, it gives us a clean and reliable way to assign rewards. After processing the observation and computing the reward, the environment calls our action controller. This module uses the vGamepad library to convert the agent's chosen action into real gamepad inputs. These inputs are sent directly to the Fortnite game client and are responsible for how the agent is able to move. On the game side, Fortnite is running our custom UEFN maps with verse scripts. These scripts control item spawners, enemy behavior, and reward cues such as HUD flashes. The game's constantly updating visually based on the action, and the next frame becomes the new state for the agent. The updated observation, reward, and episode state are then sent back to the PPO model. PPO uses this information to update the policy while keeping changes stable through its clipped objective. On each iteration, the model becomes slightly better at selecting actions. Throughout training, we log metrics such as reward progression, losses, and value estimates to TensorBoard, and we save our models for later evaluation. So the full loop is: the PPO agent requests an action, the environment captures the screen and computes rewards, the controller sends inputs to Fortnite updates the game state, and the agent learns from the result. All in all, this closed loop system allows our agent to learn directly from the visuals of a 3D game. Now that we've seen how the system works at a high level, let's take a closer look at the custom Fortnite environments that we built in UEFN. These maps form the foundation of our training setup, and each one was designed specifically to isolate and teach a single gameplay behavior. The first environment that we built is test item pickup. Even though it looks like there's only a single item spawner in the world, we actually placed over 70 throughout the map. Only one is enabled at a time, and our verse script randomly activates a new spawner after each pickup. How this works is all these spawners are stored in a verse array, and the script randomly selects an index to enable one at a time. The second map that we built is test shoot enemy, built to train aiming and shooting. Here, NPCs are randomly spawned that the agent must detect and shoot. This creates a clean and repeatable setup for training combat related behavior. And for our reward system, both maps use a custom verse triggered green HUD flash whenever the agent completes a task. Now that I've covered the system architecture and environments, we can finally get into the demo and train the agent. Here we have the Fortnite window with our agent inside the test item pickup environment, and here we have our terminal window with our Conda environment activated, and where we'll run the PPO training script. I'll start by running our command. For the purposes of this video, I'm going to overlay the terminal logs directly on top of the gameplay so you can see both the agent's actions and the training updates happening in real time. At this stage, the agent is mostly exploring and trying out random actions, slowly learning which behaviors lead to rewards. This will go on until the training iteration collects 2048 steps. And a step is one full action observation reward cycle. You can think of this as about 2048 gameplay frames, each paired with an action and a reward. And at the end of every training iteration, PPO prints out a summary of how the agent performed. As the training progresses, we can start to see the agent move from completely random behavior to more directed exploration. At this stage, it isn't reliable yet, but it does occasionally rotate toward items, walk in the right direction, and trigger a few rewards. So this current run is about 15 iterations in with roughly 30,000 steps completed. To show how the agent performs after extended training, here's one of our runs that we trained for nearly 4 hours. As you can see, the agent is no longer wandering randomly. Its movements are much more consistent and directed. Here it reliably rotates toward the active item spawner, walks straight to the item, and triggers the pickup almost every time. The hesitation that we saw earlier is mostly gone, and the policy now produces smooth, repeated trajectories. This level of consistency is exactly what we expected from PPO after enough iterations. If we open up the TensorBoard logs, we can see the progression clearly. At the start of training, the agent's reward is essentially 0. Then about 5,000 to 25,000 steps, there's a rapid learning spike as it discovers the basic pickup behavior. From there, the reward steadily increases from around 8 to over 10 and eventually reaches a long stable plateau. There's no collapse and no further signs of improvement or regression. This flat region indicates that the policy has converged to its optimal or near optimal behavior under our current environment, action space, and reward design. Any additional progress at this point would require changes to the environment or adding techniques like behavior cloning rather than simply training longer. Before wrapping up, a challenge that we ran into was reward hacking. We initially gave the agent small shaping rewards for movement and item detection. The agent quickly learned that spinning was the easiest way to win. Once we removed the movement reward and fixed the detection logic, the agent used item detection properly as a directional signal rather than exploiting it. Since our reward design was experimental, a few runs were noisy, and we even had one where Fortnite closed mid-training. It really was a lot of trial and error to get it right. Moving forward, we plan to complete behavior cloning and begin full training in our shooting environment. Thank you for watching.